Okay, welcome back, folks. We have recently looked at a bunch of different potentials and found wave function solutions to those potentials by solving the Schrodinger equation. So we've looked at the infinite square well, we've looked at the harmonic potential and the free particle, and now we'd like to look at one additional potential energy for illustration, and that is the delta function potential. So, first of all, what is the delta function? We have to remind ourselves what that even is, and so that will be the first part, the delta function. Usually denoted by a Greek letter, lowercase letter delta of x, okay, and it is basically a spike at the origin, kind of like shown here in red. Okay, so you can say that it is sort of zero everywhere except at the origin where it is infinite, loosely speaking. Okay, and the function is such that the integral over all of space of the delta function is 1. So think of the delta function as sort of the result of a limiting process where maybe you start out with some kind of pulse like that, shown in blue here, and then and let's say that pulse has an area of 1, and then you're going to shrink that pulse down along the x-axis. The width shrinks down, but the height increases, and the area is preserved. So this one here also has area of 1, and you keep doing that. You're shrinking it in width and expanding it in height, like this, okay, so as to always keep the area constant. In the limit, as the width shrinks to 0 and the height expands to infinity, you get the delta function. That's one way of approaching it. So it is somewhat of an artificial construct, but it proves to be very useful in a lot of different branches of physics. So we might as well deal with it here and now. Okay, another useful property of the delta function is the following. That is, if it appears in integral multiplied to any arbitrary function f of x, okay, then it just returns f of 0. We can generalize that just a little bit when we displace that delta function along the x-axis here, displaced to the right by an amount a, lowercase a, then instead of returning the function evaluated at 0, it now returns the function at a. Okay, so this is definitely something we should memorize. Okay. With that brief discussion of the delta function, I think we're now ready to look at the Schrodinger equation and to use that function. So we want to look at a potential energy that is of the form minus alpha times the delta function. Alpha here is going to be just a parameter that determines, you could say, the depth of that delta function or the strength of it. It determines the area when you integrate the potential energy. So the larger alpha is sort of the more significant that depression at the origin becomes. So let's take a look at that actually. So here is my potential energy, and sort of potential energy is basically 0 everywhere but at the origin where it dips down. Okay, and so that depression, that dipping down, how much of it occurs is modulated by this parameter alpha. So large alpha, stronger depression in the potential energy. We have two cases here. We have a bound state, and we have scattering states. So I have to explain a little bit what that means. Bound states occur for an energy that is negative Okay, and scattering states occur for energies that are positive. A bound state is sort of a state where the particle is going to be trapped near the origin by that potential. And scattering states are states that correspond to unbound states. In other words, where the particle is not sort of trapped in any region of space, but can travel freely. Okay, so again, here is my potential energy in purple, and then a bound state might occur for an energy down there below the x-axis. Scattering states occur for energies above the x-axis. Okay, so first we want to deal with the situation of the bound state or bound states. We'll see that there's actually only one bound state for this potential. Okay, so we want to look at that case first. And what you notice there then is that basically we have a forbidden region on the left, to the left of the origin, okay, because V is greater than E. Classically, that should not be able to happen. And certainly also to the right of the origin, we have the same situation. V is again larger than E. The purple line is above the red line. And so basically, everywhere but at the origin itself, do we have a forbidden region. Okay, only at the origin then do we get sort of what we might term classically allowed region. Okay, so when V is larger than E, what does the Schrödinger equation read? Okay, so V itself is 0 and the energy is negative. The time-independent Schrödinger equation then takes the form as shown here, where we have to just remember that the E here is a negative number. Okay, we can solve that for the second derivative, and we can write it like that. Okay, for emphasis, I've now also written it in terms of the absolute value of the energy, so that we can see that the prefactor is really positive. Okay, and we can call that prefactor kappa squared. Okay, so that kappa squared is going to be 2m absolute value of E over h bar squared. We can clearly see that kappa squared is going to be positive, as it must be. So we're thinking of kappa as a real number, a real constant. Okay, and so then we clearly see that we get exponential solutions. Both of these actually would work, e to the minus kappa x and e to the plus kappa x. Both of them work in that they both satisfy the second order differential equation above. Okay, and so we can say that a normalization demands, though, that the left side, the region to the left of the origin, x is less than 0, there we can only allow e to the plus kx, kappa x, because we do have to have that function decay away as x goes to minus infinity. And for positive x, we need to use the e to the minus kappa x form of the solution, because again, we have to have that wave function decay away as x goes to plus infinity. Okay, so we have these two regions, and they'll be described by different functions. Okay, so I just want to quickly remind you of some general rules about valid wave functions. First, the wave function itself has to be continuous everywhere, can't have any discontinuities. And then the first derivative has to also be continuous unless unless we are at a point where V is infinite. And we've seen this already in the infinite square well. The wave function clearly has a sort of a kink at the boundaries of that well, right? At x is equal to 0 and x is equal to a. If you remember back to that problem, we basically have 0 all the way for negative x's, then we come to x is equal to 0, and then we start with the sine wave. And clearly the derivative there is not continuous. It's not differentiable at that point, x is equal to 0. Same with the point x is equal to a. So the first derivative only has to be continuous in regions where the potential is actually finite. When the potential energy becomes infinite, plus minus infinite, then we don't need that first derivative to be continuous, but the wave function itself still has to be continuous. So those are the 2 points that we now want to keep in mind. We basically, from before, said that positive x is governed by e to the minus kappa x. Negative x is governed by e to the plus kappa x. But the prefactors have to be the same so that psi is actually continuous at the origin. It cannot be different constants out front. Okay, so right off the bat, we get that the wave function will have to look something like that. Okay. Now you might be thinking, we haven't made use of the delta function at all yet. How is the delta function going to enter into this problem? Okay, so we now need to turn to the origin where the delta function lives. Okay, we cannot ignore the origin, but how do we deal with it? It's not easy to deal with infinity. Well, here we make use of one of the properties of the delta function, because the integral is well behaved, right? And so the idea now is that we want to basically integrate the Schrödinger equation, left side and the right side of the Schrödinger equation, in the vicinity of the origin. Okay, so we want to integrate sort of basically starting from a little bit to the left of the origin up to a little bit to the right of the origin. We want to integrate across there. So something like this. This is my first term of the Schrödinger equation. This is the second term, and here is the right-hand side. Okay, and so now we look at each integral in turn. So here, note that the epsilon is a small number, and eventually we're going to just look in the limit where that epsilon goes to 0. Okay, so let's tackle each of these integrals separately. The first one is basically, well, you have to find the antiderivative, right? And the antiderivative is basically the first derivative of psi, because the integrand is the second derivative of psi. So you're going to be left with the first derivative of psi with respect to x, and now we have to evaluate that antiderivative at the boundaries, at the limits of integration, epsilon and minus epsilon. So that's pretty straightforward. The second integral here could be written as, well, if I plug in what v of x is, namely minus alpha times the delta function, then we get that integral, and now we make use of a property of the delta function to say that that is just equal to minus alpha times the wave function evaluated at the origin. So that one is also pretty straightforward. Now what about the right-hand side? Here I want to say that the e could be pulled outside of the integral, and then we'd be integrating the wave function from minus epsilon to epsilon, but epsilon, remember, we're going to let approach 0, so it goes to 0, and so then the width of that is 0, the height is finite. That area is going to shrink down to 0, and the integral will just return 0. Okay, so we have now evaluated all three pieces, and we can now write a simpler equation down. Namely, that minus h bar squared over 2m times the first derivative of psi evaluated at the two limits of integration is equal to alpha times psi of 0. Okay, or you can also write that of course, in this manner, because, well, yeah, I'm just bringing the prefactor over to the right. Okay, now let's take a look at the left side here. Okay, and let's just evaluate the first derivative of the wave function. Okay, when we're to the right of the origin, then we have to use ae to the minus kappa x, that form of the wave function. Take a derivative of it, pretty easy to do. Okay, and then we also let, of course, epsilon go to 0, so we kind of would like to evaluate that at 0, and we get minus a times kappa. For negative x, well, let's take a derivative again, but here we have to use the form of the wave function that is appropriate for the left side, namely a e to the kappa x. Okay, and again we let epsilon tend towards 0, and we get a times kappa. We see that this is going to be minus a kappa minus a kappa minus 2a kappa. And this here is going to be, well, minus 2m alpha over h bar squared times a, capital A, because that's the value of the wave function at the origin. Okay, and so then I have the following equation here. Okay, and I can solve that for kappa, and I get m alpha over h bar squared. Okay. We are sort of nearing our first important result here. We can also remember how kappa was initially defined, right? We introduced it as sort of a constant of convenience, so that we didn't always have to write out 2m absolute value of e over h bar squared. Now we can use that and set that equal to the previous expression, and therefore we get, for the energy, this interesting expression, minus h bar squared over 2m times this quantity squared. Okay, m alpha over h bar squared, and we can simplify that. We get minus m alpha squared over 2h bar squared for the energy of the bound state, and we only get one bound state here. That's the only solution. The energy of the single bound state. Okay, so that's a pretty nice result already, but we're not quite done yet. Okay, we have also the wave function that goes along with it, a e to the minus kappa times the absolute value of x. That is actually an expression that would work for both sides, for the entire number line x. Okay, but just to tie up some loose ends here, we can also ask what is the normalization constant, in which case, of course, I have to do this integral here and set it to 1. That integral is twice the integral from 0 to infinity. Okay, and I get something like that. This one is a fairly easy integral to do, and in the end, we end up with a squared over kappa. That has to be equal to 1 for proper normalization, and so we get that a is the square root of kappa. And finally, we can summarize, we can sketch the solution in all of its detail, right? At the origin, it will attain a maximum value of the square root of kappa, and then it will decay both to the right and to the left with a decay constant of kappa. Here's my potential energy function, okay, right there, and the energy is given by m alpha squared over 2h bar squared minus, and the kappa is given by m alpha over h bar squared. And that really now is the full solution. That's all we can know about this particular state. So we've entirely solved the problem. Okay. It's always fun to look at the solution and sort of, explore a little bit what it means, explore it in various limits. So for instance, when alpha gets very big, bigger and bigger, that means, of course, the potential is stronger, deeper and deeper potential at the origin there. And as we would expect, the energy becomes also more negative in that case. So that sort of makes sense. And then kappa gets more positive, right? Because kappa is m alpha over h bar squared. And when alpha gets bigger, then kappa gets bigger. And therefore, that means that the wave function decays away faster and is more localized near the origin. So also seems to make some sense as well. Okay, so now that we've completely solved the bound state problem, let's turn to the scattering states. So here we have that for every x not the origin, basically the particle is free, right? It does not experience any potential energy, and its energy is larger than zero, so it has some kinetic energy, if you will. So we're talking about a free particle and free particle wave functions, therefore, as well. So we have that, to the left of the origin, we have a free particle wave function. The free particle wave function, as you remember, will be given by sines and cosines, or if you want to write it in terms of exponentials, it'll be e to the ikx or e to the minus ikx. So these are the plane wave solutions we have already encountered from before, and e to the ikx would correspond to a plane wave that's traveling to the right, and e to the minus ikx would therefore correspond to a wave function or a plane wave that's traveling to the left. Okay, and so in general, we can form these superpositions as well. Some part is traveling to the right, some part is traveling to the left, and so we want to do this in broad generality, and so that's why we're bringing in all these constants, A, B, F, and G, and I'm following the book's convention here. So on the left side, to the left of the delta function, we get the top line, A and B, and to the right of the delta function, we get F and G, but they're both basically superpositions of left and right. Okay, so here we've also used k squared now as a placeholder for 2me over h bar squared. All right, so here's the picture. We have the delta function dip at the origin, and then A and B on the left and F and G on the right. So this you could interpret as the incident wave given by A, e to the ikx. This here is the transmitted wave, therefore, F, e to the ikx. This would be the reflected wave, B times e to the minus aikx. Okay, and then G we're just going to set to 0 because we don't have an incident wave coming in from the right to meet the delta function, right? We just want to look at a case where we send in an incident wave to the left. So we're going to set that G to 0, and we get something like that. Now we also need continuity of the wave function at the origin, so that implies that A plus B is equal to F. All right, so again, we have to deal with the elephant in the room here, the delta function at the origin. And in order to do so, we sort of follow the procedure from before of integrating around the delta function, sort of in that close vicinity. And without having to sort of reproduce everything now, you remember that we're dealing with this first derivative in the wave function, evaluated sort sort of just to the left of the origin and just to the right of the origin. It's sort of at epsilon and at minus epsilon. So let's just take a first derivative here, and we get IKA e to the ikx minus IKB e to the minus ikx. And when we let x go to 0 from the left, we're left with ik times a minus b. Okay, and so something similar then also happens sort of on the right. Remember, we let g equals set to 0. We set g equal to 0. And there the first derivative then is that. And when we let x go to 0 from the right, we get just ikf. Okay, and so then we take the difference between the two, and that gives me an expression like that. Okay, so we're following the exact same steps as before, but of course the results are different now because the underlying functions are different. And so that result then gets set equal to the integral. So basically minus the second integral minus the integral of the second term in the Schrodinger equation, and that again there's no difference here because the potential energy is the same. It will yield minus 2m alpha over h bar squared times the wave function evaluated at 0. Okay, and that is just a plus b. So we get this expression here, which we can solve for f. Okay, and then yield some kind of fairly ugly expression like that. Okay, so here the book does something nice, namely it introduces a new constant that makes this expression look a lot easier. Okay, we're going to start talking in terms of beta, which is nothing other than m alpha over h bar squared times k. Okay, when we use that, then we can write f more compactly in this form. So this is not very interesting now. It's just some steps, some algebraic steps here, but we want to basically solve this for b and f in terms of a. We have two equations here now, three unknowns. Let's try to maybe eliminate f first. Okay, I'm going to plug the second equation in there for the first, and basically on the right, I'm going to just eliminate f on the left rather. I'm going to eliminate f on the left. I get something like that. Okay, doing a little bit of rearranging here. Okay, I get this result here. So this basically gives us b in terms of a, and then I can plug back in. I get f in terms of a as well, and I get these two equations. So the first one is sort of dealing with the reflection part, and the second part, f, is dealing with the transmission part. Okay, so you kind of see where we're maybe headed. We'd like to know, what portion, how likely is it that this particle will just go right through, and how likely is it that it would be reflected. But here we have to remember that when we're talking about probabilities, it's always going to be amplitude squared, right? And so the reflection probability is going to be proportional to the absolute value of b squared, okay? And we can actually even go a step further and form this ratio, okay? B squared over a squared, basically, which actually in terms of beta gives us a nice expression, beta squared over 1 plus beta squared. Okay, and we're going to call that a capital R, and we call it the reflection coefficient. Okay, so that is the reflection coefficient, and we can do something very similar where we form the ratio of f squared over a squared and call that T for transmission coefficient. When we plug in, we get a very nice compact formula for that, namely 1 over 1 plus beta squared. Okay, and so there are now nice expression for r and t. We also see that r plus t is 1. So this gives us sort of now a probability of one of these incident particles being reflected versus being transmitted from the delta function at the origin, the inverted delta function. So all that's left to do is really substitute back what we know beta to be, right? So we can plug in for beta and we get these two expressions now. These are very easy to obtain by basically just substituting beta back into the previous set of formulas, and we get something like that. Okay, and notice that they have the same structure, only in the denominator, the second term is flipped for the transmission coefficient. Okay, and so here again, we want to just make sure that these formulas make sense in some kind of limit. So what about when the energy of the particle, the incident particle, gets very, very large? Well, when E gets very large, you can plug that into the expression for capital R, and you see that R is going to go to 0. Plug it in the expression for T. Okay, there we see that T is going to approach 1. So for very large energies, we basically have no probability of being reflected, and we're going to definitely transmit through. And of course, the reverse is also true. When E gets small, still positive but small, then we have much higher probability of reflections. We can also look at how these two coefficients depend on the alpha, and we note that it actually depends only on alpha squared. When alpha squared gets large, then the reflection tends towards 1 and the transmission tends towards 0. That kind of makes sense too, because from one point of view, because when alpha squared gets very large, then the disruption at the origin becomes more noticeable, right? The delta function becomes stronger. So that sort of makes some sense too. Here I just want to draw your attention to the fact again that the results only depend on alpha squared and not on alpha. And this is actually not the case. This was not the case for the bound state, where a lot of the bound state actually did depend on alpha, not alpha squared. For instance, the kappa, the decay constant, depended on alpha. So here, to summarize, here we get that, well, we have this incident wave in blue here. It's approaching the origin where there's a delta function waiting there for it. We're going to get some reflection possibility and some transmission possibility. And those probabilities are actually completely unchanged when the delta function flips up. So when the sign of alpha changes, we get no change in the reflection and transmission coefficient. So that is an interesting tidbit here, is that you could flip the sign of alpha and not change any of the results. So the blue sort of squiggly line, the blue plane wave that approaches the origin from the left, it really doesn't matter to it whether it sees a barrier like that or a depression, a dip. Okay, in both cases, will the likelihood for reflection be the same? Okay, and so in the case of the barrier, the positive delta function, we can say that the particle can just tunnel through that barrier at a probability given by the transmission coefficient T. So this would not be possible classically, of course, but quantum mechanically, we can tunnel through and arrive on the other side. Okay, thank you.